Yes.
Hi everyone, I'm Dan. This is Roy Lippman from FalkorDB. Today we want to show you guys user-defined functions, which we've recently added to our product. And we're going to look at a very cool use case, farm to table, and explain how you can create your own functions and run them inside of FalkorDB. All the links that you see, as well as the documentation, will be made available in the links at the bottom of this video. And without further ado, Roy, take us away.
Thank you, Dan. Let me quickly switch over to our presentation
Great.
and we'll get started. Okay. So UDFs are, stand for user-defined functions. This is a relatively new feature within FalkorDB, but the concepts of UDFs has been around for quite some time now. Um, Different database vendors had introduced this capability, usually in order to bridge the gap between user requests and the built-in functionality within the database. So, for example, it's not uncommon for users to say, oh, the built-in functionality or the built-in functions in the database doesn't include some very specific function that I need. Can you accommodate for that? Whenever we're getting such requests, we need to take into consideration if the request is valid, does it serve the general public? And if the answer is yes, then we would be happy to add new functionality as a built-in function as part of the database. But sometimes the request is too specific and we just either cannot accommodate or it would take us too long to add this new functionality. And UDFs basically gives you the power or the ability to implement whichever functionality that you want or need inside the database. Um, so I think they're extremely powerful, especially if UDF have some type of lower level API to interact with different components in the database. And that's pretty much what we've done. So, um, so UDFs in FalkorDB, the way that we like to think about them is not as a standalone function. We like to group UDFs together under what we refer to as a UDF library. So you load a UDF library, and the library contains one or hopefully multiple functions. In this example, we have the collection utils UDF library, and within it there are 4 different UDF functions: intersect, union, shuffle, and zip. So that's the way FalkorDB manages and structure UDFs. In FalkorDB, we've decided to go with JavaScript as our engine and programming language for our UDFs. Within a user-defined function, you have access to every single data type that FalkorDB supports. This includes both the primitive types like strings and other scalars, in addition to array and dictionaries, but you also have access to graph primitives like node, edge, and the path object, and those specific objects has additional functionality or additional APIs that allows you to interact with them. This includes the graph traversal API that you can use within your user-defined function in order to traverse a graph. And this maybe also leads into another reason why one would want to use UDFs, and we will demonstrate this during this call. FalkorDB and other graph databases, most of them support a query language known as Cypher. And Cypher has its limitations in terms of how do you define pattern matching or graph traversal. If your traversal is very specific in the way that it expands from one node to another, let's say you have some very complex condition which you need to check in order to perform your next hop or not, Cypher might be either very difficult or just impossible to conduct such traversals. And so UDF make this very easy to perform. So that can be done with the graph traversal API. Last thing to mention about UDFs, let me go back here. UDFs can call one another. So all of the UDF functions are visible to one another. And within FalkorDB, you can manage multiple graphs all under the same database. And so UDFs are not imported at the graph level. They are shared across the entire database. In addition to them being replicated in case you're working with a cluster, and they are persistent in case you're loading your data from a backup file. Just so you know, additional information about how we manage and work with UDFs. Enough with the introduction. Let's jump right into an example which we will be using in order to demonstrate UDFs. So we start out with this idea of an application which helps us move produce like fruits and vegetables from a farm all the way to the customer, getting them at some local store. And so the graph which we will use in order to demonstrate this is composed of just 3 different types of nodes. We would have the farm node where the produce are made. Then products are moved from a farm to at least one hub or multiple hubs until they reach the store. So farm, hub, and store, these are the node types, and we have just one type of edge in this design, which is just connected to. So this is the graph topology. And as I said, the thing that we're trying to achieve here is to find a path going from a farm all the way to a store, moving through maybe multiple hubs along the way. And we want to make sure that the produce are delivered as fresh as possible. Here's just a bit more information about the metadata which we will be working with. And so an edge have a travel time, so how much time would it take a truck, for example, to move from maybe a farm to a hub. In addition, what is the average temperature that that is measured along that path or along that edge. In addition, a hub, a processing hub, has a processing delay. So how much time does it take the produce to leave that hub to the next next leg? And this is, I think, this is all of the metadata that we have here. Okay, to compute the freshness level, we have this formula. So at the very beginning at the farm, the produce have a freshness level of 100. And along the way, the produce decay. The formula says that the decay or the freshness level is 100 minus the sum of each leg along the way, taking the travel time times the average temperature divided by 10. That's the edge component, right? The travel time and the average temperature. And then we deduct the delay. So that's the node component. How much time does the produce are waiting to be processed in the hub. So we have this formula. So here's an example computing the freshness score of this particular path. So it's 100 minus whatever values we had there. The computation says that along that path we're gonna get a freshness score of 73.7. All right. Now we're dealing with a kind of a pathfinding question here, and a nice thing about this is that we can basically place a threshold saying, given this path, if the freshness level is below a certain threshold, disregard this path because we want to maintain a higher freshness level. So this path might not be the right path for us. With pure Cypher, it would be extremely hard to prune paths as they're being computed. It's hard to try and get from a farm to a store and say, oh, I do not meet the freshness requirement, so discard the subtree from this current node, which, if we would be able to prune out or to quickly disregard path, then the overall performance of this lookup would be much faster. So in Cypher, it's practically impossible to do, but with UDFs you can definitely do that, and that's what we're gonna show in the next example. So just to run through this slide, we start from a farm, we're getting to a hub. We see that just reaching this hub would give us a freshness level below the threshold, and so in UDFs we can just say, don't bother exploring the subtree spanning from this hub because it would not meet the requirement. Maybe there's another path which will. Last thing before we move on to seeing some source code. In addition to finding a path, we want to compute how much is it going to cost us to deliver the produce on a given path. So we have this another formula which would compute the cost. And so the cost of a leg, or if you want to think about the cost of the entire path, is like so. It's gonna cost us $10 if the travel distance is less than 50 kilometers. If the travel distance is more than 50 kilometers but less or equal to 200 kilometers, it's gonna be the distance, half of the distance. Otherwise, it's gonna be the distance times .4 plus 50. In addition, if a leg is the truck that delivers the produce on a specific leg is refrigerated, then we're gonna add 20% to the cost of that specific leg. So finding a path and also computing the cost. All right, let me move to an actual graph which we would be working with. So in this graph we have 3 farms colored in purple. And then each farm is connected to at least one hub. And some hubs are connected to others. And on the left here, we have our 3 different farms. So this is the graph which we would be working with. Let me move on to the actual UDFs. All right. So we have 3 different user-defined functions. Each one is written in its own JavaScript file. So we have calculate path cost, we have find freshness path, and lastly we have generate manifest. Don't bother about their content, we would review this shortly. I just want to show you how you can load UDFs into your FalkorDB database. So this is a simple Python script. It reads the content of each one of those files, and it basically bundles all of them together into a single string. And then it uses our UDF load function within our FalkorDB client. You need to specify the library name. Remember, FalkorDB likes to work with UDF libraries. You need to provide the library name and then the content of the library. So a bundle. If everything works fine, we're gonna see UDF loaded, and then we can use the UDF list function in order to see which UDFs are available in our database. So let me do just that. Sorry about that. Load UDFs. Okay, UDF loaded. Farm to table, that's the UDF library name, and we have 3 different UDF functions that we can use. Perfect. Let's start with find freshest path. That's the algorithm, the UDF, which finds the freshest path between a given farm and a given store node. And this is the implementation. Before we go into the details of the implementation, I want to show you one thing that's worth mentioning. In this JavaScript file, we can have as many functions that we want. We don't have to expose all of those functions to the database. The functions that we want to expose, meaning you can access them or invoke them within a query, are those that are registered. And in order to register a function, we have this global Falkor object that has a register function. And you need to call this register function for each function, UDF function that you want to expose. It accepts a name under, that's the exposed name. Usually it would have the same name as the actual function, but it doesn't have to. I could name this XYZ, and then I would be able to invoke find freshest path by calling XYZ. But it usually makes sense to keep the same name. So this is how we're registering UDF functions with the database. Now, the actual implementation. So this function accepts a start node that would usually be a farm node, a target node that is probably going to be a store node, and a threshold, which we will be using in order to prune paths that do not meet that requirement. So for example, you might say, don't bother or disregard paths that are not able to achieve 60% freshness value. And the way that we're going to go about this is with a a multi-source BFS type of traversal. So we're actually starting here. We're calling traverse from the start node. And the start node is a node object, which means you can actually access the node attributes by just accessing it as if it was, a field of a field of a JavaScript object. So start node dot initial freshness would actually fetch the attribute value from the node. This is, I believe, the visited list, or so this is going to be the path. At the moment we have no path, so this is an empty array, and this is the visited list, which is required by DFS and then BFS. We don't want to revisit nodes that we have already visited. So we enter this function and we check if the current node that we're at while we're constructing the path is the same as the target node. And we're using, once again, access to the node metadata. In this case, we're using the ID. So if those two nodes have the same ID, that means that they're the same node. And if that's the case, we've reached our target, and we want to see if the current freshness is better than the maximum freshness that we've already found. If that's the case, we've actually found an improved path. And so we update the best path and we return. Otherwise, meaning we haven't reached our destination, then we're using this get neighbors function from the current node. This is part of the traversal API. Given a node, you can ask to get its neighbors. So that's what we're doing here. And we can specify if we want this function to return nodes or to return edges. We can also specify the direction of the traversal. In this case, we want just the outgoing edges from the current node. So here's the edge list. And now we run through each one of the edges. This is an actual edge object, and we ask for its target, meaning the node that this edge points to. That's our neighbor. We're adding the neighbor to the visited node list in order not to explore it in the future. And now we compute the decay, or we update the decay by looking at this edge. So the transit decay would be, according to our formula, it's going to be the travel time, the edge travel time times the edge average temperature divided by 10. That's the edge decay component. And now we also have the node component. So the processing decay, that's going to be our neighbor processing delay if this is a hub, or 0 if it's not a hub. And finally, we recompute the current freshness. This is the new freshness, which is the current freshness minus the transit decay minus the processing decay. And this is the part where we can actually do the pruning. If the new freshness is lower than the threshold, then we log. And this is another thing to notice. FalkorDB has this log function that you can use to debug, or to print whatever you want. So you can think about it if you're a JavaScript developer or something similar to console.log. So if we're not meeting the standard, then we just disregard this new frontier and we move on to the next one. Otherwise, if we're still above the threshold, then we're adding the edge to the, one moment, visited node, and this is visited node. Oh, this is a check. So this was a check to see if we haven't seen this node before. If we did, we skip it, and in here we add it to the visited node array. We push the edge and the node to the path, expanding the path, and we recurse from this new frontier. After this recursion's return, we're backtracking, meaning we need to pop the frontier. So we're removing both the node and the edge from the path, and we continue on. And that's pretty much it for find the freshest path. So let's actually see this in action. We have this, let me see, find path, find freshest path. Yes, we have this query. Let me just copy paste this over here. And let's see. What we're doing here is we're saying in Cypher, find the farm with the name Mountain Orchard and find the store named Downtown Market. This would be the start node and destination node. And what we want is to return the farm, the store, and here you would see a UDF invocation. We need to prefix the invocation with the UDF library name, which we've called it farm to table dot find freshest path, and we pass in the farm, the store. Our threshold is gonna be 65, and the function returns, let's see, the function returns a dictionary with a path object, so a path key containing the actual path, and the freshness. And in this query, we don't care for the freshness, we just want the path. So let's run this. Here we go. That's the freshest path computed by the UDF. It starts out at the Mountain Orchard farm. It goes through this edge with a distance of 120. The travel time is going to be 3 hours. The average temperature is 15, and not surprisingly, the path is refrigerated. We will wait for 3 hours at the Arctic cold storage for processing, and then the produce would continue on 200 kilometers, traveling for 3 hours in a temperature of 2, and this is going to be refrigerated to get to this hub, and finally taking the third leg, which is quite short and the temperature is quite low, reaching the store Downtown Market. All right, now let's see the calculate path cost UDF. So similarly, we see the registration. The function is going to be exposed under the name calculate path cost, and that's the actual function. It receives an array of edges, the actual path, and it will compute the cost according to the delivery cost formula. So here it is. For every, the total starts with 0, and then for every edge we get the distance, and we get the is refrigerated attribute, which is Boolean. And the edge cost is, according to the formula, 10 if the distance is less or equal to 50, half the distance if the distance is less or equal to 200, or it is dot 4 times the distance plus 50 if it's more than 200. Lastly, we're adding 20% if the leg is refrigerated, and we accumulate the path cost, and finally we return it. So that's another UDF which we will be using. Let me see if I have a slide for the manifest. So think about the situation where you want to expose the freshest path in addition to the path cost in a JSON style or JSON formatted output for maybe some other component in your application to consume. So this is what I call a manifest, which summarizes the entire delivery path. And so, yes, you can use Pure Cipher to formulate this, but it's a little bit easier to do that with UDFs and JavaScript. So that's the last UDF which we will be looking at. Once again, we're registering it. The generate manifest gets, you pass in the output from find freshest path. So this is the freshest result. We're expecting to find the path object or the path array in it, and we're basically iterating through the path, extracting the current node and the edge. We only care about the edges in the manifest, so we're just accumulating the edges, and each, you know what? No, we care about both the edge and the node. We group those into what we call stops. So a stop would contain the node name. It's probably going to be a hub. The type of the node. So another thing to know, this is a node object has access to its labels. So we extract the label. We extract the distance. This information resides in the edge, and we care about whether or not that leg was refrigerated or not. Finally, that's the delivery report. We have a status, we have the final freshness, which we also extracting from the freshness result. We call another UDF. So from this UDF, we invoke the calculate path cost UDF, and this is why we've accumulated the edges. So this UDF would invoke another one, and then we have this route summary. So let's see the generation of this manifest. So here's the query. Let's run it. We're working with the same farm, mountain orchard, and the same store. We project the farm, the store, and we run the find freshest path UDF. We call this result, and finally projecting back to the caller the manifest. So we're invoking the manifest given the find freshness path result, and we're returning the manifest. So let's run this, and let me move to this view, which I should be able to expand. Yeah, let me run this in my terminal, which should be a little bit easier to view. So give me one moment. Let me see. One sec. Okay. Okay, here we go. So here's the manifest. Delivery report, status, success, final freshness, 90.4. Estimated cost 204. Route summary. This is the first stop. Going from the farm, we're gonna reach Arctic cold storage. It is a hub. The distance to it is 120 kilometers. The leg is chilled. From there, we're gonna reach Air Freight Hub. Once again, it's a hub. The distance to it is 200 kilometers, and the leg itself is chilled. And this is the last stop, downtown market. It is a store. The distance to it is gonna be 50 kilometers, and the leg is chilled. So that's the end-to-end example of using UDFs in order to find a farm to table freshest path. A few things to mention before we wrap this up. Our documentation under docs.falkordb.com, there's a section for UDFs explaining how you can write one, how you can load, update, delete, in addition to the different data types that are supported and the capability and functionality of each one of those data types, and the actual traversal API. Lastly, we have our UDF library, which we call Flex. It's a collection of different functionalities grouped by category. So we have functionality for string utilities, for collections, map, similarity, temporal, and bitwise, which we've written. So just to give an example, let's see, docs. Let's go to collections and let's have a look at shuffle. So here's the shuffle UDF. The way that you would invoke it is by specifying the UDF library name, which is Flex, and then the category, which is collections, and then the actual function, which is shuffle. It expects a list and it would shuffle the elements in the list. Flex is the intention is for it to be community driven, so we're happy to accept any contributions. Hopefully we can extend it with the help of the community. And with that, I believe that we're pretty much done. The entire demo that we've run through is available online. Here's the link to it. And I'll be available on Discord if you want to reach out or have any questions. I'm gonna return things back to Dan in case, Dan, you want to share anything, and if not, that's also fine. Thank you.
No, that was very good. So like Roy said, everything is of course available on YouTube and on social media, as well as in our blog and the documentation. We encourage you to join our Discord community to post questions and share the projects that you're working on. And if there's any contributions that you'd like to make, the best way to reach us is the website and Discord. And with that being said, if you haven't already subscribed to the event directory that we have on Luma, that way you get notified when an event like this gets scheduled and you'll receive an invitation before we send it out to everybody else. And with that being said, thank you, Roy, for your time, and let us know what kind of UDFs you're going to build.
Thank you, Dan. See you
Thank you,
next
Roy.
time.
Bye, guys.
Bye.
Get started, Roy. The first question we got was, why are UDFs implemented in JavaScript? Why did we choose to do that?
There were a number of different reasons why we've decided to go with JavaScript. The first and foremost, I think it's related to security. At the end of the day, we're going to allow you to run arbitrary code or scripts in the database. So we needed to choose a platform which would be secured. And this is usually means sandboxed. And so when thinking about maybe sandbox solutions, I think that the number of different options come to mind. But I think that the most dominant one is JavaScript. Um, and also, I should mention that we had some past experience in former companies that we've worked in that specific type of feature where we've brought in some type of an engine, and we've tried a bunch of those. Um, I think that the conclusion was that JavaScript is the best solution, both in terms of sandboxing, security, performance, and expressibility. So I think this is why we've gone with JavaScript.
Excellent. I would have said something, but I want to make sure we have enough time for everyone's questions. So I'm just going to put the next one over here. And I do this, guys, because some are just listening in and don't have their monitors on. So the next question is, have we got any kind of MCP server available right now? Answer is yes. But Roy, do you want to expand on it?
Um, I know that we have one, but I don't feel like I have enough information to answer that question. Maybe if one other uh, of our panelists want to take this, great. Otherwise, we're gonna have to circle back on that.
So yeah, the short answer is yes. I will send links to the MCP server that you can get started with. So if there was a follow-up question somebody wanted to ask specifically about which kind of server or what you can expect to do with it, please drop it in the comments and I'll take that. But the short answer to this basic question is yes. Let me pull up the next question. How are the user-defined functions accessible or manageable in SDK? So I want to make sure I fully understand. But do you fully get it, Roy? I'm not sure which SDK is referring to.
Yeah, I think I understand the question. So, as with any other functionality in FalkorDB, we expose all of those functionalities via commands. So whenever you're sending a Cypher query, you're executing the graph.query command, which might have subcommands associated with it. And that's exactly what happens here with UDFs. We have added a new command called graph.udf, which has a number of subcommands under it. We have graph.udf load, graph.udf list, graph.udf remove, I believe, and graph.udf flush. Now, usually you're not sending commands manually, and so all of our official clients have this UDF functionality. We've seen the Python client during my demo, and you should use those client UDF functions to work with UDFs, either list them, load them, replace them, delete them. That's how we're expecting users to manage them. Oh, I should mention that similar to obviously graph data being replicated and being persisted, the same goes for UDFs. So if you're running in a cluster and you have loaded your UDFs to one node in the cluster, then your UDFs are being replicated. If you're using a persistency file for backup, that would also include your UDF. So if you're restoring your database from backup, this will include all of your UDFs. So they are replicated and they are persisted.
Super. Just following up to the person that asked about the MCP server. So here it is. Of course, as a link will be sent after this call. I want to jump to another question. think it's a good one. So the question is, I am hosted. I'm imagining you have a hosted cloud account with FalkorDB. Is Flex already on my instance or part of my instance?
No. First of all, UDFs are quite new, so you're gonna have to run the latest version of FalkorDB on the cloud in order to have all of the UDF capabilities. Now uh, we've decided to go against bundling Flex as part of the database. If someone wants Flex, they're gonna have to download the flex.js script. It is published on Flex GitHub repository, and they're gonna have to do graph.udf load Flex or use one of the clients to load it. From that point on, it should persist, and you can use whichever utility within Flex that you want. But it doesn't come bundled in with the database. You're gonna have to manually load it.
Of course, guys, whoever posed that question, if there's a follow-up, happy to take it. The next question, Roy, is, are UDFs replicated and persistent?
I guess this question came before I have answered it. Yes, yes, and yes.
Yes, indeed. Perfect. So the next question is straightforward. Can I use, I imagine he says, can I use this? I imagine he refers to everything we showed. Can I use this in Python?
So this I need some elaborations.
Yeah,
Um,
I think it's
you can interact with UDFs via Python, yes, but you cannot write UDFs in Python. The engine which runs the actual functions is a JavaScript engine. So no, the UDFs needed to be written in JavaScript. But all of the interaction with the database, sending queries, loading UDFs, what have you, can be done in whichever client language that we support, including Python.
awesome. Roy, just give me 1 second because questions are piling up in both the chat and the Q&A. Let me make sure I don't repeat myself or pitch a question that we may have already covered or answered. Regardless, guys, we pull everything you send us, and what we do afterwards is we answer all the questions and we put them in our blog, so you can go and revisit the answers that we've given here. So if we don't get to your question, don't worry, we'll answer it afterwards and send across a copy that you can read, in addition to the recording and everything that you see here, the repos and examples that Roy showed on screen. It's all free and available within 24 hours after we cap off today's session. 1 second, let me pull up the next question. So the next question reads, if we have multiple graphs in the same cluster, will user-defined functions be available on all of these graphs?
Yeah, this is a good point which we've struggled with at the beginning. It was a design decision. UDFs are cross graphs. They're not associated with a single individual graph. Once you've loaded a UDF library in, it is available throughout the entire cluster for every graph. And I think that the reason behind it were situations where users who are managing hundreds or thousands of different graphs would have had to load over and over again the same UDFs for each one of their graph if we've, went with that decision. So at the time, I mean, currently the design is UDFs are available cluster-wise to every graph managing the cluster.
The next one is as follows. Please, why are we not making room for TypeScript?
I do not object to it. I think that the restrictions come from the engine that we've put in place. The engine that we're using to run UDFs is called QuickJS, and I don't believe it supports TypeScript. If it does, or a different, version of it comes with TypeScript support, then we should get it out of the box. But to the best of my knowledge, the current version that we're running with QuickJS doesn't support TypeScript.
Victor, I didn't skip your question. Hope that answers it. And of course, if there's a follow-up, drop it in the comments. The next question is as follows. How how big can a UDF function, I imagine it's how big can it get? And can I store data inside?
Yes, you can store data within a UDF. You can do with it everything that you can do with just plain old vanilla JavaScript.
Mhm.
Um, it's not running in the browser, right? So there are some restrictions, but for the most part, everything that you can do with JavaScript, you can do with UDFs. We have not restricted the size of a UDF script. We did restricted the execution time of a single UDF call, and we've also restricted the size of the stack or the amount of memory that a single UDF can consume. This was done for safety mechanisms to make sure that the database is not um, being affected um, or becomes unresponsive due to an abusive UDF.
Excellent. I'm going to squeeze every minute we have to answer those questions. So the next question is, are there any limitations to UDF or Flex? A bit of a broad one, but I think we covered a little bit of that in the beginning, but maybe if we can just recap some of the limitations that are currently, that people maybe should take into consideration when trying to implement.
Yeah, so except for what I've just mentioned in terms of the memory consumption and the execution time, this feature is relatively new. We did added the ability to log, and we've added some traversal functionality to UDFs. What we haven't done just yet is to give a really broad set of graph interaction functionality. Uh, Especially, UDFs cannot perform any write operation. So you can read and you can get access to any um, data that is part of your graph, nodes, edges, attributes, relationship types, labels. But a UDF at the moment cannot create node, delete nodes, create edges, delete edges, update attributes. Every write operation, those cannot at the moment be achieved via UDFs.
Excellent. I'm just going to answer this question real quick. The question is, did we talk about the improved performance that UDFs, I will imagine UDFs will introduce compared to regular methods? So yes, Roy did cover that, and we show that when we're calculating the freshness of the farm to table. I believe it's at around minute 20 of this video. So when we release the recap, skip over to the point where Roy compares the two methods.
Maybe I do want to add to it.
Yeah, go ahead.
Um, it really depends on the use case and the query, but UDF do have an overhead. Remember, FalkorDB, when it executes a pure Cypher query, go through tons of optimizations, and the code is written in a way that is really high performant. A UDF has the overhead of first transitioning data from FalkorDB built-in type system into JavaScript. So this is one overhead that you're gonna pay for. Just pushing in arguments from Cypher to JavaScript. Then there is the other way around where you're returning data from UDF. There's the second conversion from JavaScript to FalkorDB native types. And lastly, the JavaScript engine, QuickJS, as fast as it, is, it still runs JavaScript and I believe it's running in an interpreted manner. So usually, it would not be as fast as a regular Cypher query, but there are some situations like the one that we've shown where using UDF opens a new avenue or gives you a new ability, which translates to better performance. So it really depends on the situation. It really depends on what you're doing. In some cases, it would be faster. In other cases, you might see it a little bit slower.
Super. So next question is, are you considering allowing Rust-based UDF in the future?
Never say never, but but it's not on the roadmap at the moment. No, we've just released this JavaScript version. I don't think we would at the moment spend time introducing Rust as a engine for UDFs.
Cool. The next question I think comes up quite frequently since we've released this, either on calls or questions that we get. So how is FalkorDB UDFs compare to Neo4j's? Is it only the fact that it does iterative graph traversal, or are there other advantages? Hard question.
So yeah, I mean, we started this UDF feature to bridge situation in where users ask for functionality that we said either it would take us too long to implement or it doesn't make sense for us to implement, and but we wanted them to to be able to have that custom functionality in. And I think that the same thing happened at Neo4j a few years back with their ability to run custom logic and introduce Epoch, which is the Neo4j version of Flex. I should say that Neo4j UDFs are written in Java. You need to compile a jar, you need to upload a jar. It feels, to me, it feels like a bit uh, more tedious to get those UDFs in. In our case, it's just a the JavaScript script that you need to upload, and then you can either remove it if you don't need it anymore, or you can easily update it. There's no compiling involved. You don't need to send files over or place files in a specific directory and have the server pick them up. I feel like the way in which UDFs are implemented in FalkorDB is much easier. And over time, the Flex library would have a wide coverage similar to what Epoch has, hopefully with the help of the community.
Yeah, I think it's a good point that the fact that we are open for community contributions and an encouragement that should come out of this workshop is for you guys to, first of all, give it a try, give it a look, and if you can contribute, we would greatly appreciate it. This brings up to exactly an hour, Roy, and I had a nice time. I think we covered a lot of ground. There's a lot of questions that we went through, and I think there's a bunch more that are in the chat that we are going to have to answer offline and send you guys via email, blog, Discord, our regular distribution channel, all of the questions and the VOD. I hope you had a great time and you learned how to leverage UDFs with FalkorDB for whatever it is that you're building next. And if there's one key takeaway I want you guys to leave with here tonight or this morning is the possibilities that this essentially unlocks for your next project. The entire team is very excited to take your call after this. If you have a project you need help with or you want to share with us, if there's any help that you need to get started with graphs or just any consultation whatsoever that we can give you, we are very much available, Discord, website, or LinkedIn. And we do this monthly. You should expect an invitation to the next workshop on a subject either like this or something more to do with RAG, which, judging by the questions, seems to be a popular topic that we should probably speak about more. But until then, I was Dan, this was Roy, and we'll see you guys in the next Graph and Rag Talk session, which will be the 12th in the series. Have a great day, great evening, and it was really nice to have you with us. Thanks, Roy.
Thank you, guys. Thanks. Bye.